Okay, so in the field of thermodynamics, which really is what causes everything, is energy movement of energy or heat. We have a huge deal to deal with what's called enthalpy. It is a thermodynamic property, and it's equal to the sum of the internal energy and the product of pressure and volume. So it actually, in a way, ought to include two things. The symbol for it is H, but in chemistry, we simplify it. We deal with keeping the pressure constant, so we can only deal with one part of it. We don't have to deal with both parts. It's really hard to measure like the total energy or the total enthalpy. So a lot of times what you'll find is that we don't calculate H, we calculate delta H, because it's easier to measure a change or a flow of energy than it is to like try to get the total energy that's in something. So as long as the pressure does remain constant, this is actually kind of key, then the only part of this enthalpy that's left is this change in the internal energy due to heat flow. So if you can go away from any work being done by expanding gases or anything and keep the pressure constant, essentially the enthalpy becomes the energy that's received or given off as heat. And so when we say delta H, and I have a bad habit of calling it the heat change, well, one of the reasons is even though its name is enthalpy, and the H doesn't stand for heat, it really doesn't, but it can as long as pressure remains constant. Well, if you think about it, that's normally how things are done in a lab. We just do it in an open container under constant pressure, and it works. So because of this fact, the enthalpy is also by a lot of people called just the heat content, and delta H is then just thought of as the change in the total heat content or whatever thermal flow takes place in or out of the system. So it does simplify our life just a bit. So, well, I want to throw out here a quick review of what the first law of thermodynamics is. It basically says that the total energy of a system and its surroundings remains constant. So essentially, you know this is true, that we cannot create or destroy energy. So you do get this conservation idea. A sort of a different twist of looking at it is the change that's in the energy of a system. Like, okay, so let's have a sealed system, and we're going to try to change its energy in some way. It equals the heat flow into the system. So let's say I have a closed gas and I put heat in. If it expands and does work on its surroundings, then the net total internal change was zero. Because even though I put heat in, it did work as a result. And so it's a wash. The two canceled each other. And so for a lot of chemical things, unless you got a lot of gases involved, especially in sealed containers, our pressure doesn't change, and the work done by the system then is zero. And then the change in energy is just the heat flow. And so if you look at this way, this is how we do usually use it in chemistry. Delta H is just the heat flow, like we were talking about on the previous page. It's kind of an important deal to catch that. Generally, internal energy depends on heat and work, but we can kind of get around that in chemistry a lot of times. So even though we can't create or destroy energy, as you know, it can change form. You can go from nuclear energy, kinetic energy, which is movement, potential, which is a lot of stored forms that can be there. You can stretch a spring and store energy. You can have chemical reactions that make molecules that store energy. You can have a lot of that. Random heat energy, electrical current movements. I mean, you just go on and on. Light, another form of energy. And the reason that this little statement right here is important is that it deals with the second law quite a bit. So let me move on here to the second law. But before I do, let's take a look at a couple properties that I think some of you have already figured out. If the sign on this is negative, then that means energy is going out. If the sign is positive, then it's got to be flowing in. And this kind of thing is true all the time, whether it change chemical, physical, whatever. Any change that occurs is going to either have heat going in or out. It will. So like, melting or something may not be chemical, but there is, still heat involved. And this is a really kind of instructive little thing to look at right here. If you look at this first process right here, I've got H2O liquid becoming H2O vapor. You'll notice that the energy change for that is positive, so what that tells you is heat's got to go in to do this. The other one also has a positive change of enthalpy, you can see here, but it's quite a bit larger. positive 286 kilojoules per mole compared to 44. So take a minute here and just look at this and notice what's similar and what's different. All right, so hopefully, if you think about this just a minute, the amount of enthalpy that's involved depends on the amount of chemical that's involved. To boil water, which is the top process, it's about 44 kilojoules per every mole. So if I want to boil 2 moles of water, this is a property we got to realize. It's going to take twice the amount of heat energy, which is pretty logical, but good to keep in mind. The other one there is the breaking of the water covalent bonds, like getting the things to go away from each other so far that they're no longer bonded. That takes a lot more energy than just making the water go from a liquid to a gas. So that's why those numbers are very different. The other important thing to remember is that doing a reaction the other way will change the sign of delta H. So, like for example, what happens with the heat flow if you're going to condense water? Or if you're going to make water from its elements, which would be the reverse of the bottom one, and hopefully you can see that those signs would change. In order to condense water, energy would have to be given off, be negative 44. And in order for to go backwards in the top one, in other words, make hydrogen and oxygen go blow up and explode like they like to do and make water, of course that's going to release a bunch of energy. So the sign becomes a negative and it switches signs. So these diagrams that we sometimes like to draw for processes that are having energy in or energy out, as you can see here, we started out at reactants at a high enthalpy, and that drop to products was a giving off or a reduction in the amount of energy. That would be what we call exothermic process. An endothermic process is exactly the opposite. Now, in reality, you got to be careful. These two graphs are a little too simple, I should say, for what really often happens. There is another factor that we will get into in kinetics when we study rates. If you look, the delta H right here is just the difference between the reactants and products. That's what it is. It's a total energy difference between where you start and where you end. The little hump in the middle is, for example, even though water wants to be formed from hydrogen and oxygen, I usually have to put a little spark or something there to get it to happen. Most things do this. There's got to be enough collision or enough input of energy or something to get the thing going. That is not part of delta H. It's called the activation energy, and like I say, it's a big thing in kinetics. In thermodynamics, which is this section, we often only concern ourselves with the change of enthalpy, just from where did I start to where did I end, and we don't get into the activation energy. It's not included in that. I would also just point out on my second graph here that the reactants were at a low place and the products were at a higher place, so we got like a delta H that's an input or a positive number, like for an endothermic reaction where energy goes in, and the activation energy for that is really, really high. Now delta H is still just the difference between where you start and end, but it is why these kinds are hard to go. So as you can see, there's no intent in me continuing to teach during this time, and that's far enough for now anyway. So thank you, Ms. Trues.